Welcome to the Calculus, a collection of micro lectures, video lessons, and sample exercises. Let's derive the rule on differentiating a quotient of functions. For this video, we are going to show the property or theorem or rule about differentiating or finding the derivative of a quotient of functions. Generally, it states like this: if f and g are functions, and let's say h of x is equal to the quotient of f of x and g of x, but g of x cannot be equal to 0, and if the first derivative of f of x and g of x exists, then the derivative of h of x is equal to this rational expression. We have the product of g of x and the first derivative of x minus the product of f of x and the derivative of g of x all over the square of g of x. Yes, this is what we are using in finding the derivative of a quotient of functions, or also known as rational functions. But we need to show it here, the validity of this proof, so that we can use it further in our few examples. Now, this proof or video may take long, and this may need a lot of concepts, but please bear with me as we are going to show that from h of x being the ratio or quotient of f of x and g of x, but of course g of x not be equal to 0, so that our given function is defined. We will have the form here, h of x. We are going to show that from that we're going to show that the first derivative of h of x is again this form here, minus f of x. Take note, it's minus, so the numerator cannot be interchanged, unlike the rule on product, because that's addition. But this case, again, we cannot interchange the terms of our numerator over the square of whatever be the original denominator, or g of x. So this is the definition. Let's say a of x, its derivative is the limit of this notation, a of x plus delta x minus a of x all over delta x as delta x approaches to 0. Or other references uses h instead of delta x. We have here the limit of a of x plus h minus a of x over as h approaches to 0. These are just equal to each other, and take note the h here is not the function h already given. So we're just trying to show the two forms, because other references or books uses the second form because it's easier to manipulate. But for this, let us simply use the original definition, as it includes increment of x or delta x. It involves even the smaller variation on the value of x. Okay, so we're going to show that from here that this is equal to that using this relationship, okay, using the definition as well. So here's the proof, and again, we might need a lot of space here and probably an extra page if we look into the need later, but of course please bear with me. So let's start with h prime of x, or the derivative. Per definition, you have the limit of h of x plus delta x minus h of x all over delta x as delta x approaches to 0. Per definition, instead of a, we have here h. Now, before we proceed, we cannot subtract this and say we can cancel that because we have h of x here, because they are both functions. So let's what do you call this, represent them using this given idea here. So for h of x, it's the ratio of f of x and g of x, right, as given. In short, if we have h of x, sorry, that's x plus delta x, this must be the ratio of f, sorry, let's do it right here. We have here f of x plus delta x, as we simply interchange the notation over g of x plus delta x, where this is now not equal to 0 as well. Okay, we are going to use this because we will have to substitute these forms here and here so that we can operate it further. So please bear with me. You will have this form now, the limit. Let's do it right, because we will have a rational nested rational expressions. So you have here the limit, because this will become a rational expression. So you will have here f of x plus delta x over g of x plus delta x. That's just this notation. Minus your h, which is f of x over g of x. All over delta x as delta x approaches to 0, right? Okay? By substituting the equivalent forms of h of x and h of x plus delta x. Let's combine the expressions on our numerator. The LCD will become g of x plus delta x times g of x. Please bear with that. And of course, as you look into that and here, when you combine the similar fractions, you need to apply the notations properly. So the LCD of the numerator alone is g of x plus delta x times g of x. And then you will have to divide this by this. So you will have g of x times the numerator. So you have f of x plus delta x times g of x minus this now to be divided with that. So this is what remains. That will be multiplied to your f of x on your numerator, g of x plus delta x. Okay? These are still all over delta x as delta x is approaching to 0. By the way, we are doing this because we don't want this to be 0 because everything will become undefined. The limit of that will become infinity or undefined. Yeah. So continuing on our numerator, take note of one of the techniques in nested when we use nested rational expression, because this is called nested because on a given rational expression, one of its part is also a rational expression. So hence nested rational expressions. This is how we do it. If we have here 1/2 to be divided by 3, we usually do it like this. We copy the first or the numerator and we use the keep, change, flip method. Okay, so we change the operation. We keep the numerator, we change the operation to multiplication, and we flip the denominator 1/3. This is the keep, change, flip method when dividing rational expressions, right? So we keep the numerator 1/2. Instead of division, we change it to multiplication, and we flip this or we reciprocate the denominator. Similar thing here. So you have the limit. We keep the numerator, the entire numerator, f of x plus delta x, okay, times g of x, all over, so this is 1, minus f of x times g of x plus, sorry for that, delta x over delta x. We kept the numerator. Instead of division, change the operation of multiplication, and we flipped your sorry, my bad. This is not all delta x because we are still using this for our numerator. G of x plus delta x times g of x. And then now we change the operation to multiplication. Instead of this, it becomes multiplication, and we flip the numerator, the original numerator. So reciprocate that 1 over delta x. Keep, change, flip method, right? Let us not multiply this in the meantime because we will return to that later. The next part here is this. I would like you to listen this carefully. Since I need to simplify this, take note of our target. The target goal is this form here. So we need to structure forms like this, okay? But we have a combination of f and g in our numerator and denominator. So what we can do here is this. I would like to introduce here 0. Yes, I will add 0. Okay, what's the purpose of that? By adding 0, it doesn't change the value of the entire expression. But once I add 0, I can change it into two different expressions which are additive inverses, just like 1 and negative 1. Okay, 1 and negative 1 are additive inverses. So once I introduce 0 here, I can place here 1 minus 1, and it doesn't change the value of the given expression. 0 could also be 2 minus 2. We have ak squared minus ak squared. Or here, I would like to introduce here 0 being equal to the product of two functions f and g, minus f and g. This minus that is just 0, but when I add them here inside, there is an important implication to that can help us further simplify this. So this is how it will look like. So please bear with me again. We have the limit of, I will just write here delta x upon 0, so partner with that because I need to focus here on writing the correct forms. Take note, I'm not multiplying this yet. So we have f of x plus delta x times g of x. Okay? I'm going to start with minus. I'm going to start with this. Minus f of x times g of x. Why I'm doing that? Because I have here g of x and g of x. I could move out or factor later, leaving this negative, which is again the goal of the definition. We have negative here. So you really need to apply important properties to see what needs to be done and what needs to be added or combined here. Now I'm adding minus. I'm going to add the positive to neutralize that. F of x, g of x. This is entirely equal to 0. Okay, so it doesn't matter. We're not changing the value, but we are introducing that to formally a factor. Okay, I'm going to erase this. Okay, leaving this alone. Okay, because I still need to write here minus. Let me erase this notation here. The remaining, this one here, the remaining form, you will have minus f of x times g of x plus delta x. Okay, they're all under, okay, g of x plus delta x times g of x, still to be multiplied with 1 over delta x here, which we have not multiplied yet because there is an important concept that we are going to draw to that later. Okay, the purpose again of multiplying, adding these two, so that we can factor g of x and g of x here, and as you look on the other side, we have f of x and f of x here. So this is how it goes, continuing that, the limit. And let me write this first part over that. It should be lastly written, but I'm going to write that so that I could focus on what I need to do here. So factoring g of x, as I remove g of x here, this is what remains, and minus this what remains. So times f of x plus delta x minus f of x. Okay, for the second, I would like to factor out here minus f of x, not positive, because I would like to make this positive and this negative, because as I take here minus g of x, take note that this is plus, so I'll take negative, what remains on the inside will be negative, so it will become minus g of x. Okay, let me move this down. Alright, and continue with the next. As I factor out minus f of x, this is times, okay, this will be positive, and the implication for that is I can interchange these two terms now, which would help me design a form again similar to the definition where this is positive and this alone is negative. So this is now negative and this is positive, hence I'm doing it right as I factor minus x. Okay, so to complete, they are still all over g of x plus delta x times g of x, again times 1 over delta x here outside. Okay, now I could apply other methods to do this, but let me try to return this form as I multiply it here. Now I don't want to reappear that here because simply it's just multiplying that as what I have mentioned earlier. But let me do things like this. I'm going to show you a proof of what I'm going to do here. Consider this expression that I'm going to present to you. 3/4 times 1/2. Actually, this is just equal to 3 times 1/2 over 4, where we multiply the entire fraction to the numerator only. Here's the proof. Because as you consider this further, that's 3/2 over 4. By the keep, change, flip method shared earlier, this will become keep, change, and you flip your denominator. And since multiplication is commutative, you can rearrange your denominator, so 3/4 and 1/2. Showing this is really equal to this form. That's my point here, okay? I'm showing you this because instead of multiplying this by the usual method where this will reappear here, what I would like to do is to only multiply this to the numerator only. Just like this one here, the 1/2 is only multiplied to 3, the numerator, which is again, they are just equal to one another. So here is the next step. Let me, hopefully it's clear to you. I'll be using another page for the next parts, but hopefully this is clear to you. Or, okay, let me copy this entirely, and we will have the next page to take care of this so that you will always review to this part. Okay, this is the next page. I'm pasting it here, the entire discussion of what I'm going to do. So what I'm going to do here is this. Okay, so I've been multiplying this entire expression only for the numerator. Okay, so you have the limit of g of x, this grouping. Let me do it like this. Okay, don't worry about that, I'm just doing it earlier. Okay, making this shorter. Okay, times f of x plus delta x minus f of x here. Okay, as I will be multiplying. Sorry, I wasn't able to see the space. Move it down. Okay, take note as you multiply this to your new, sorry, take note as you multiply this, you have to multiply it here and here as well. So this will be multiplied by 1 over delta x. Okay, 1 over delta x, this entire expression. Okay, minus the second f of x. Let me interchange them. So I will have the same format as the definition here. Okay, so you will have to start with g of x plus delta x positive, and since this is negative, so minus g of x times 1 over delta x now. Okay, they're all over g of x plus delta x times g of x. Take note, again, this was only multiplied to your numerator, hence distributing it into our two terms, and the denominator here is still the same. Just like again, what happened to 1/2 is multiplied to 3, leaving 4 as itself. Because the next part here is this, as delta x approaches 0, is what will happen here. Okay, you will have nested. We are returning to a nested form. Okay, the item that we were able to what do you call this one, revise earlier, but now we return to that. G of x, f of x plus delta x minus f of x. Okay, over now delta x. As I multiply 1 to that, this would be its new denominator, minus f of x times g of x plus delta x minus g of x. Okay, all over delta x, right? Okay, all over now g of x plus delta x times g of x. Still, we cannot apply the limit because even if there's no delta x here, there are delta x's here on our nested rational expressions. Hence, our numerator would be a difference of two imaginary numbers or undefined numbers, so we can't do that. But the point of sharing this is here. What will happen to this? What will happen to this? They corresponds to the definition. This definition, I'm going to copy the definition here. Okay, let me copy this entire form so that we will be guided on our target and the definition. Let me paste them here. Erase the unnecessary scribbles. This other version. Okay, and then moving that here because this is our target. Okay, this is our target. This is our target. This is the definition. Look at the definition and the item I emphasized here. They correspond to the definition, as we will have limit here later because we can apply here limit theorem. And the limit theorem goes like this. Okay? So limit theorem goes like this. Let me remove this in the meantime. Clip. I'm going to paste it later because I will be applying here a limit theorem. The limit theorem allows us to distribute the limit to both terms, and since there is also a limit theorem, there is a limit theorem for difference, but there is also a limit theorem for what do you call this one, product. So what we could do is this one here, distributing the limit for all the terms, the limit of g of x times the limit of f of x plus delta x minus f of x. Okay, think of that. Minus the limit of f of x times the limit of g of x. Sorry, I am choosing the delta x rather here. Okay, think of that. Then g of x plus delta x minus g of x over delta x here. Take note that the limit as delta x approaches 0 for all. I'm distributing that using limit theorems. All over, I'm also doing that on our denominator. Limit of g of x plus delta x times the limit of g of x. Okay? I'm doing all of this so that, again, I have this notation and this notation as well. I am returning what I have deleted earlier. Paste. Alright. I have returned to what I have cut or clipped earlier. Okay. So, notice that this too follows the definition. Hence, they corresponds to the derivative of a. But since this is f and this is g, they corresponds to that. Now, we will have this next form and we are now closer to our result. Sorry for a very long proof because this is really a really long proof. You have the limit of g of x as delta x approaches 0 times now this is just f prime of x. Okay, f prime of x. Then minus the limit, this the next term, minus limit of f of x as x delta x approaches to 0 times this is just the derivative of g. Take note, we are close. This is derivative, right? Sorry, I forgot the notation was removed once we have copied it earlier. All over the limit of g of x plus delta x as delta x approaches 0 times limit of g of x. I don't have much space here. I might need another space, but definitely I can talk about the next step here. Since we don't have delta x here, we don't have delta x here, the limit of that is just g of x itself times f prime of x. Okay, minus the limit of f of x as delta x approaches 0. There's no delta x, so it's just f of x times g prime of x all over the limit of this as delta x approaches 0. That's 0, so that's actually g of x times the limit of this as delta x approaches 0 is also g of x. We have two g of x's here, so we can simply combine them. Hopefully it's clear. We can combine them as the square of g of x. This is finally the intended goal of our h of x. Okay, going back, we started with h of x. So if you would like to come up with a conclusion, I still have a space here. Let me have our final say. Therefore, h prime of x is equal to, moving this lower, this form now, g of x, the final form, times f prime of x minus f of x times g prime of x. Again, they cannot be interchanged because this is subtraction all over the square of g of x. Finally, we are done with our proof. Sorry for a very long proof because there are a lot of concepts that needs to be added here. And since we have proven this already, in the next few videos, we can use this to differentiate quotient of functions or differentiate rational functions. Thank you very much for watching. So what are you waiting for? Subscribe now.